Hey guys, and welcome to Chem Squad Chemistry. Today we are going to be covering Unit 3, which is the trends of the periodic table. Hopefully by this point you've already found our slideshow on our website and you have learned some about the periodic table. Hopefully you know the names of each of the groups of the periodic table, the difference between a group and a period. You maybe even know some definitions like the effective nuclear charge, shielding, and a few other things that's found in our PowerPoint. If you've not already taken a look at that PowerPoint and learned those things, please do that now before watching this video. So we're going to jump straight into it. We are going to talk about our first trend, which is, so let's go ahead and get started talking about the atomic radius. Atomic radii. The atomic radii is simply the distance between the nucleus and the outermost electron energy level. So the distance between the nucleus and the outermost electron energy level. Hopefully this is already making a little bit of sense to you. From math class, you probably learned that the radius is from the center of the circle out to the very edge. No different. This oddly looks just like an atom. And we're going to be measuring the distance from that nucleus all the way out to the outermost energy level. Hopefully when you see the outermost energy level, you think of something called valence electrons. Remember, those are the electrons found on the outermost energy level and the only ones that are involved in bonding. So we're not really concerned with the lower energy levels, only the highest one that each atom has. So let's go ahead and decide what our trend is going to be. If you have a periodic table handy, it would be good for you to go ahead and draw these trends out so that you don't forget them later when you're looking at them. If you could draw an arrow across the top of your periodic table, just like this, that's going from right to left, and we're going to write increasing. That's telling us that as we move from right to left, the atoms are getting larger. And as we move from the top to the bottom, going down a group, they are also increasing. So moving from, say, hydrogen, which is the top of group 1, down to francium, they're getting bigger and bigger and bigger. And from these arrows, you can see the overall trend is pointing down towards the bottom left, where francium is. Francium is indeed the biggest atom on the periodic table. And the opposite of that would be the smallest, which is helium, which is, way up here in the top. It's all great. You can already start to answer questions about this. Like if I were to ask you, what is the larger atom, aluminum or chlorine? You would find them both on the periodic table. You can see that chlorine would be about right here. Aluminum would be over here. We follow our trend knowing they're getting bigger going this way. That tells us aluminum is our larger atom. We can also answer questions in a group. Let's say we're looking at magnesium and comparing it to barium. We can say, okay, which one's larger? And just by knowing our arrows, we can say barium is the larger atom. And it's great that we're able to do that so easily, but we're going to, on the next slide, actually describe why is it that these atoms are bigger than each other? What causes them to be larger, or what causes them to be smaller? So we are going to be comparing these three elements to each other. You notice that beryllium and fluorine are in the same row, which we call a period, and you notice that barium and beryllium are in the same column, which we call a group. So we're going to be comparing the two of them. Let's go ahead and start out with comparing beryllium to barium. So these are the two we're going to be comparing. If I were to ask you which one is larger, you can simply just remember the trend from the periodic table and tell me barium is the largest one, but sometimes you're going to be asked why. So let's look at what we know about barium and beryllium. Beryllium happens to be in what period? Period 2. So that tells us that beryllium has 2 energy levels, which looks like this. Correct? Has 2 energy levels. It's in the S sublevel, so there's circles just like that. Whereas barium is in what energy level? It is in energy level 6. We know that because it is in period 6. So it is going to have 6 energy levels. Yes, I'm sorry, 6 energy levels. 4, 5, 6. So just by drawing this simple representation, you can see that barium is much larger due to its energy levels. So if someone were to ask you to talk about why is it that barium is bigger than beryllium, you could talk about its energy levels and say how barium has much more energy levels and much more electrons than beryllium does. It's just like the analogy I've used before, putting on coats and layers of clothing. The more layers of clothing that you put on, the larger your body becomes. If you put on a shirt and then a jacket and then a bigger jacket and an even bigger jacket, you become larger and larger. Same thing's going on with these energy levels. The addition of energy levels causes an atom to be larger. That explains why our trend exists as we move down the group. All right, let's go ahead and discuss our next one, which is why is it that beryllium and fluorine have a relationship? If someone was to ask with those two, you know the trend shows us that beryllium would be larger than fluorine, but this draws many questions. But fluorine has more electrons, it has more protons. So let's go ahead and take a look at beryllium and fluorine and see what we know about them. Beryllium and fluorine appear to be in the same period, which is period 2. So if we were to draw them, we would say that both of them have 2 energy levels. At first glance, it appears that these atoms would be of the exact same size because of their energy levels. But there's something else going on here. Hopefully you've already learned the definition of effective nuclear charge, which is the pull of a nucleus on its electrons. We know that beryllium and francium do not have the same charged nucleus. Beryllium is number 4 on the periodic table, which tells us it has 4 protons in its nucleus, where francium is number 9, tells us that it has 9 protons in its nucleus. You can see fluorine has a much stronger nucleus than does beryllium. So what is going to happen here when we put this very powerful nucleus down here in these energy levels? These valence electrons are going to be pulled more tightly to this nucleus because of how strong it is, whereas beryllium does not have as strong of a nucleus, and they are going to be able to be further away from it. Remember that Coulombic attractions do exist within an atom, which is the positive attraction and the negative attraction. Here in chemistry, we call that the effective nuclear charge, how the nucleus affects those outer electrons. So if someone was to ask you, why is it that beryllium is larger than fluorine, you would talk about the effective nuclear charge and how it pulls its electrons in closer. Our next trend that we're going to be talking about is shielding. This one is probably one of the more simple ones because most of us are familiar with what the word shielding means. The best example that I have to talk about this is to imagine a refrigerator and a magnet. Right? If you were to take this magnet and you put it close to the refrigerator, it's going to stick right to it. Right? There's nothing between the refrigerator and the magnet. However, let's imagine that you got a 100 on your chemistry test and you bring it home and you want to show it to your parents and you put it there and you take the magnet and you go to put it on the refrigerator. There is now a little bit of paper blocking the pull of the refrigerator and the magnet. That's what we call shielding. Now let's imagine that you're a great student and you get lots of A's. You come home and you want to put all those papers in the same spot on the refrigerator, right? Many papers here on the refrigerator, blocking the pull of the magnet on the refrigerator. If you were to take this magnet and try to stick, say, a packet of papers to the refrigerator, it would just fall right off. What's happened is the attraction of the magnet and the refrigerator has been blocked from each other. Now this happens in atoms as well. As you know, the Coulombic attraction of the nucleus and the electrons pull on each other. So when shielding takes place, there's going to be some blocking going on by lower levels. So let's go ahead and draw the trend of shielding. Draws a little fake periodic table again. Something like this. Shielding is going to increase as we move down, just like in atomic radius, increase. But as we go across a period, it is going to remain constant. And we are going to talk about why. So an easy way to draw this is just to draw two simple lines that look like this, showing us that it is constant across a period and increases as we move down. So this time we're going to be using the example of lithium, nitrogen, and potassium. Let's go ahead and start with the easy explanation, which is why it remains constant across a period. We can see here that lithium and nitrogen are in the same period, which is period 2. So if we were to draw them, they would have two energy levels that look just like this. So you can see because they have the same number of energy levels, it's going to be the same number of shielding. There is only one energy level blocking the pull of the nucleus on the valence electron here in lithium, and there's only one energy level blocking the pull of the nucleus in nitrogen to its valence electrons. So simply because they have the same number of energy levels, their shielding will be the same. Now that's a little different for when we go down a group, because we already know that as we move down a group, we are adding energy levels. And if you haven't figured it out by now, as you add energy levels, your shielding is going to increase because you're blocking the nucleus. So let's go ahead and compare lithium, which has 2 energy levels, to potassium, which has 4 energy levels because it is in period 4. As you can see here from our atomic radius trend, potassium is much bigger than lithium because of the energy levels. If we want to talk about the shielding, we can see that potassium's nucleus is very far away from its valence electrons. It has 1, 2, 3 energy levels blocking that effective nuclear charge, whereas lithium is going to only have 1 energy level blocking the effective nuclear charge. So as we move down a group, the addition of energy levels causes the shielding to increase. The extra electrons are blocking the effective nuclear charge. All right, let's go ahead and talk about our next trend, which is known as electronegativity, probably a word that you've never heard. But the electronegativity is the measure of the ability of an atom to attract electrons. So this really all comes down to knowing what a Coulombic attraction is. Remember, that is the attraction of the positive nucleus on the negative valence electron. All right, so that's the definition of effective nuclear charge. So let's go ahead and draw our trend on a periodic table so that you can at least know that. Electronegativity is actually the exact opposite of what we've learned about atomic radius. It is going to be increasing as we move from left to right over towards fluorine, which fluorine is the most electronegative element. Remember that noble gases are in this last column and they are already stable, so they don't attract electrons as much. And it is going to increase as we come up. So the exact opposite of the atomic radius trend. So here, if I were to ask you who is more electronegative, rubidium, which is over here, or iodine, which is over here, we would say, oh, it must be iodine because it's to the right of rubidium. Or I could ask you who is more electronegative. Is it zinc or is it mercury? We would assume that it is zinc because it is above mercury on the periodic table. Basically, you're looking for whatever element is closest to fluorine, because fluorine is the most electronegative element. It attracts electrons quite a bit. So for our example for this one, we're going to be looking at these 3 elements, lithium and fluorine, which we know are in the same period, period 2, and lithium and sodium, which are in the same group, which is group 1. So if I were to ask you which one is the most electronegative here, hopefully you've caught on that it is fluorine. But remember, our trend moves over to the right across a period and up a group. So fluorine is the most electronegative, but lithium is more electronegative than sodium. Let's start with the group this time and compare lithium to sodium. We already know that lithium is the most electronegative, but the question becomes why. If you were to imagine this taking an electron and putting it in the dead center here of lithium and sodium. Think about which way would this electron be more likely to move. Is it more likely to be attracted to the positive nucleus of sodium, or is it more likely to be attracted to the positive nucleus of lithium? Hopefully you're thinking back about, shielding. Shielding plays a huge role here. Even though sodium has a more powerful nucleus with 11 protons, whereas lithium only has 3 protons in its nucleus, sodium also has all of this shielding going on. So because of the shielding that is happening, this electron would be more attracted to lithium because it can feel the pull of its nucleus, which we call the effective nuclear charge. So simply put, lithium is more electronegative than sodium because it does not have as much shielding and it can feel the pull of the nucleus more, which we call the effective nuclear charge. All right, so let's go ahead and take a look at our next example, which is a lithium being compared to fluorine. As we've already discovered, fluorine is the most electronegative, but let's talk about why. Both of them are in period 2, which means they have 2 energy levels. So we need to decide which one of these is more likely to attract an electron. You should have already learned that metals don't attract electrons. They form cations, right? Cations like to give away electrons, so there's you a little hint. Fluorine is a nonmetal. It has 7 valence electrons, and it needs to attract one in order to become stable. So, you could talk about that, how fluorine always forms ions to become stable, whereas lithium will not. Another way that you could think of it is the exact same way we just talked about it with increasing as we move up a group. Imagine if we put our electron in the dead center. Who would it be more attracted to? We notice that the shielding is the exact same. It's the exact same. Each one of them have 2 energy levels shielding us from the nucleus. So we know the energy levels aren't going to play a role. The thing that plays the biggest role is actually that effective nuclear charge. Who is this electron going to feel the pull of most? Is it going to feel the pull of fluorine's nucleus, which has 9 protons, or is it going to feel the pull of lithium's nucleus, which has 3 protons? Well, I hope that you're thinking it's going to feel the pull of fluorine's nucleus because that is a stronger magnet. It's going to be pulling this negative electron over here to the more powerful nucleus, which is exactly what electronegativity is, the ability of an atom to attract an electron. So because the nucleus of fluorine is much stronger than the nucleus of lithium, it's going to feel the pull of fluorine more, especially since the shielding is the exact same. All right, so our fourth and final trend is ionization energy. As you can see here, ionization energy is the energy that would be needed to remove 1 electron from any given element. So we're talking about, let's say, we have hydrogen here, which has 1 electron. How much energy would it take for us to come up and just take that electron away? That's what ionization energy, the energy needed to remove an electron. So let's go ahead and draw the trend on the periodic table, just like we've been doing. It is actually the exact same trend as electronegativity. They go hand in hand. So it's going to increase as we move up a group, and it's going to increase as we move to the right across a period. So again, these elements over here have the highest ionization energy, whereas these in the bottom left-hand corner have the lowest. So if I were to ask you who has the most, we compare potassium to, say, nickel. You would say, well, since nickel's to the right, it has the highest ionization energy. If we compare, say, potassium to beryllium, you would say, oh, beryllium has the highest ionization energy because it's further up. So we're going to be comparing, we'll go ahead and talk about these 3 elements and see how they differ from one another in their ionization energy. So we are going to be comparing beryllium to magnesium and magnesium to silicon. We see that beryllium and magnesium are in the same group, so that should tell us something about them, as well as we see that magnesium and silicon are in the same period. So keep in mind that silicon, as we move to the right, it should have a higher ionization energy than magnesium, and beryllium should also have a higher ionization energy than magnesium, just because of the simple trend that we've already learned. But first, let's go ahead and talk about beryllium and magnesium. Beryllium happens to have 2 energy levels, and it has 2 valence electrons. We know that because it's in group 2. Magnesium has 3 energy levels, and it has 2 valence electrons. So I bet with what we've already learned about effective nuclear charge and shielding, you guys could tell me which one of these would be easier to take an electron from. Hopefully you're thinking it would be magnesium. Magnesium would be the easiest to take an electron from, and we can talk about why. One of the reasons is shielding. Look how much shielding there is between the nucleus and these outer electrons. So these electrons aren't feeling that effective nuclear charge that much. They're further away. There's lots of shielding going on. So the energy I would need to take that away is relatively low. Let's look at beryllium. It only has 1 level of shielding. So these electrons are feeling the pull of the nucleus more. So it would be a little harder for us to take that electron. So if you need to compare why ionization energy is higher at the top of a group, it all has to do with shielding and how the shielding is blocking the effective nuclear charge. Now, if we want to compare it as it moves across a period, that's a whole different story. Let's go ahead and look at the difference between silicon and magnesium. So magnesium and silicon both are in the same period. That means they both have the same number of energy levels, which is 3. We already know, that silicon is actually a little smaller than magnesium because it's pulling its electrons in closer, and that's going to play a role here. Magnesium has 2 valence electrons. Silicon has 4 valence electrons. It's not going to play a huge role this time, but it's interesting to think about it. Silicon has a nucleus that has 14 protons in it. 14 protons. And magnesium has a nucleus that has only 12 protons in it. So even though there's not a huge difference here, we can see that the effective nuclear charge is going to be greater over here with silicon, meaning that the nucleus is much stronger, so it's going to pull its electrons in closely. So since the nucleus is stronger, these electrons are going to be held on to the nucleus more. So it's going to require quite a bit of energy to pull it away from that nucleus. Over here with magnesium, we have the same amount of shielding, right? We have 2 energy levels, but the nucleus is much weaker. It only has 12 protons. So because of the weaker nucleus, the lower effective nuclear charge, we can now take this electron more easily. And that has it for the 4 types of trends. These trends are also outlined, and the definitions are written on our website in the PowerPoint. If you have any additional questions, you could either see me, Ms. Spivey, or Ms. Bennett, and we will help you as much as we can. Have a good day.